Hi there, thanks for joining us. This is a Q&A edition of Space Nuts, where we talk astronomy and space science. And in the Q&A episode, we answer questions from our audience. We've got a whole bunch today. We're going to hear from Jeff, who wants to discuss the effect when the sun goes red giant, which is going to happen in a couple of weeks. No, it's not. Blue is asking about accretion disks. Julian about the expansion of the universe. And one of our old favourite topics from Peter, dark energy. That's all coming up in this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And back again to furnish us with his wisdom, or just to have a couple of lucky guesses, is Professor Fred Watson, astronomer at large. Hello, Fred.
How are you doing, Andrew? Good to see you.
Good. And you?
Yes, firing on all cylinders as far as I know.
That's all right. Although back then they only made them with 3 cylinders, didn't they? Oh, gosh. I'm in a wicked mood today. Sorry about that. Yep. Okay, we better get on with it. Now, I will put out an appeal, like I did at the end of the last episode, for audio questions. Questions in general, but audio questions particularly. We are desperately short, and we don't know why. It's just a weird quirk of fate, I suppose. But if you would like to send us some audio questions, you can do that on our website, spacenuts.io, and click on the AMA, Ask Me Anything tab at the top, and send us the message. Don't forget to tell us who you are and where you're from. Our first question, Fred, comes from Jeff in Fayetteville, Arkansas in the United States. Hello, gentlemen. Oh, he's wrong for a start. I mean, come on. I happened upon your podcast several months ago and enjoy it very much. Last month, you discussed the thought experiment having to do with what would happen if to the rest of the solar system if the sun suddenly disappeared. My question's a little bit more concrete. In 5 billion years or so, our sun is expected to swell into a red giant before perhaps collapsing into a white dwarf. What will this do to our sun's total mass, and what effect will it have on the outer planets that survive being engulfed, Earth not being one of them, as it turns out? A follow-up question. Are other suns dying throughout our galaxy responsible for the rogue planets far out in space between stars that I've read about? Thank you for your time and the stimulating discussions you allow me to listen into. Thank you, Jeff. That's lovely. A few questions in there, Fred. Yes, our sun, which we have talked about going, ballistic in about 5 billion or so years. What happens to the outer planets?
Yes, it is a great question, and I think the sort of implicit assumption is that the inner planets are not going to be around.
No,
which probably will include the Earth and possibly even Mars. So the process towards the end of the sun's life, and somewhere in the region of 3 to 5 billion years. I think the process starts about 3 billion years hence. So it's a little bit earlier than Jeff says. So I hope that's not a cause for alarm. 3 billion years.
He's at his watch, so he's going to have to reset back, and that's always a pain.
Yeah, it is. That's right. Yeah. The other day dutifully set the timer to time down on my phone, because I had to take things out of the oven, and it got to the end of the time and didn't do anything. Just stopped. I did too.
My phone suddenly decided to put all calls through to voicemail before I even know it's ringing. Picked it up the other day and thought, why is it vibrating? And then I realized my sister was ringing me, but it was making no sound. There was no indication. It just filtered. And when I pushed a couple of buttons, eventually found her. And she said, "Oh, yeah, I was just listening to your message."
Well, there you go.
Voicemail message.
Which is not a problem we'll be really worried about in 3
No, not
years'
just
time. Because,
but if anyone knows the answer to that, please let me know.
Well, I can tell you the answer. You have a smartwatch, and that rings as well.
Well, I don't think I had it on at the time. So.
Anyway, so yes, the inner planets get swallowed up as the sun swells. It doesn't happen suddenly. It's a fairly leisurely process. There is a collapse of the core down to a white dwarf star, which is the end product is this white dwarf star, which is the size of the Earth, but with quite a lot of the mass of the sun still tucked in there, and an outer shell of expanding gas. And if we were looking at that from the outside, we'd call it a planetary nebula. So that outer shell of gas is hot. It's hot enough to basically vaporize the inner planets. But Jeff's question's not about that. It's about how do things look from the outside. And so the outer planets, interestingly, their orbits will be perturbed, which means changed, but maybe not as dramatically as you might think, because that swelling, what it's doing is, if you look at the center of gravity of all that, it's still at the center of the solar system. Even though the outer layers of the star, and there's a significant amount of mass in that, even though most of the mass is going to be concentrated in the white dwarf star, but the outer layers are expanding, you're outside that zone. So to you, the center of gravity, center of mass of the solar system remains where the sun is now. And so the effect on the orbits of the planets might not be as dramatic as propelling one of them out to become a rogue planet. So it could be a lot gentler than, a supernova is different. If it explodes, then you're talking about dramatic and cataclysmic events that would certainly disturb the orbits of planets, although some planets seem to be able to survive that. We can see supernova remnants with planets chugging around. Anyway, this scenario is that there may still be planets which will be outside the envelope of the red giant. Now, eventually, that envelope is going to pass the outer planets and may evaporate them as well, depending on what sort of temperature it is. But so the red giant phase, the outer planets might be still okay and still say it's stable. But once it progresses beyond that and you get to the planetary nebula stage, where the outer layer is light years in diameter rather than just a few 100 million kilometers in diameter, or trillion kilometers in diameter, then you're probably in trouble if you're on the outer planets as well.
Okay. How long does that process take to reach that nebula stage?
It's relatively slow. You're talking about billions of years.
Wow.
Yeah. So there must be a collapse phase for the nucleus. I'm not an expert on these, like what we call highly evolved stars. But as it goes from red giant to a planetary nebula, that's when you change into a white dwarf in the middle. You've got the nucleus of the star collapsing. So these are the end products of normal stars, actually. A normal star will go through this phase. A massive star will become a supernova. It will explode.
Wow. Okay. So you pretty well answered everything in one hit. The white dwarf will have the same mass as our sun at the moment, more or less. So it won't really have an impact on the outer planets until after the halo effect over billions of years, and probably not enough effect to cause rogue planets.
I think that's right, yes. I think evaporated planets is more likely.
Yeah.
So rogue planets are most likely formed either just formed in gas clouds collapsing into stars. These are things that aren't big enough to collapse into stars, though they become little planets on their own, or by being ejected because of a gravitational influence. If you get two planets that pass very close to each other or something like that, one of them might get booted out of their solar system.
There you go, Jeff. Hopefully that answered all of your questions. We like multifaceted questions. It takes us off in all sorts of strange directions sometimes. Great to hear from you. Hope all is well in Arkansas. Fred, our next question comes from Blue. He's from London. I have a question about accretion disks. Given that gravitational time dilation causes time to pass much slower near a black hole relative to Earth, why does the disk appear to move at high speeds to us? I would have expected the material to look like it's moving at extreme slow motion or even stop moving the closer you get to the event horizon. Love the show, guys. Thanks, Blue. Okay, I know you're going to know the answer to this one because I think we've had a similar question before, but it seems to be an ongoing theme with black holes. Why do we see things that we don't think we should see?
So yes, the accretion disk is actually quite a long way from the black hole, and a lot of that swirling material is ejected from the black hole rather than getting sucked in by the magnetic fields that the black hole generates. It sort of projects the accretion disk material at very high velocities to the sort of north and south of the accretion disk. So there will be a time dilation effect. I should check this as to how much it would be, but I think the overarching point is that you're far enough away from the event horizon that time dilation in the accretion disk is not great. It's not high enough. I think it's all a matter of scale rather than being a matter of the phenomenon, which I think Blue's right. I think he's, anything that gets close to the black hole's event horizon is going to show up a time dilation phenomenon.
I suppose it would also depend on what kind of black hole it is. I mean, some of them are massively massive.
The massive, yes, that's right. That's correct. So a supermassive black hole will produce a bigger phenomenon. I'm just going to try looking something up to see if I can put any detail on that. Which I should have done.
I'm helping you a lot here.
Yeah, okay. All right, here you are. Here's a number. For a 10,000 solar mass black hole, and that's that's the kind of limit of what we call an intermediate mass black hole, something measured in tens of thousands of solar masses. For a 10,000 solar mass black hole, the time dilation of the accretion disk inner edge is only 22%. So it's what I've said. It's the scale of the process that makes the difference.
Fair enough. Okay. Simple answer, really.
Yeah, seems to be.
All right. Thank you, Blue. Hope you're going well. Love London. Only been there twice, I think. Twice, yes. And really enjoyed my time. It's a beautiful city. Really love that place. I'd go back tomorrow if I could. Thank you, Blue. And this is Space Nuts. You're listening to it with Andrew Dunkley and Professor Fred Watson.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Space Nuts.
Next question, Fred. Hey, nutters. Julian from Brampton, Ontario, Canada here. What is causing the expansion of the universe? Oh, that old chestnut. I mean, are we a black hole eating outside matter? Or are other fundamental forces responsible? Or are the forces actually keeping us together? Part 2, I think we're up to part 4 actually. Part 2 of this question would be, Fred mentioned the universe is expanding slower. Does that mean we know exactly how fast the universe is expanding? And does that mean speed's faster than light? I hope you all got that. Love the show. Thanks, Julian. Oh, he's packed in a lot there in 3 or 4 sentences. What's causing the expansion of the universe, Fred? And I know the answer to this one.
I think, the way we usually interpret the Big Bang is in the beginning there was nothing and then it exploded.
Yeah.
And that's kind of more or less what it was. And so we're still seeing the aftermath or the effect of that explosion in the expansion. So it's driven by some fundamental injection of energy at the start of the universe. We can kind of quantify how much it was. It's a very large number that set the expansion in motion, and it's still going on. Now, the second bit of the question is the interesting bit, part two. Let me just, yes, there are a number of parts here. Are we a black hole eating outside material? Some scientists have suggested that we are within the event horizon of a black hole, and that's
I've heard
what's causing the expansion of the universe. It's a very speculative idea. It's not one I'm very fond of because I think we need a bit more hard evidence as to whether that black hole's there. Are we a black hole eating outside material? Probably not. Or are there other fundamental forces responsible? Well, yes, maybe. And that comes to the second bit of the question. It says, Fred mentioned the universe is expanding slower. That's actually not the case. It's expanding faster all the time, but that acceleration is reducing.
Yes.
So the
Expansion a conundrum, isn't it? Right?
It is.
We thought it was expanding at a faster rate, but now it's expanding faster, slower.
Faster, slower, that's right. Before we used to think it was expanding at a slower rate. We used to think in the 70s and 80s that it was slowing down. The expansion was slowing down, and one day there'd be perhaps a reversal of the expansion and a big crunch. Then in 1998, along came Brian Schmidt and Saul Perlmutter, and between them they figured out, and Adam Rees, of course, the 3 Nobel Prize winners in 2011, they figured out that actually the expansion is accelerating. And that's still the case today. That is the situation we have. The expansion is accelerating, but there is now new evidence that suggests that the acceleration is reducing. So it's not that the expansion of the universe is slowing down, it's that the acceleration of the expansion of the universe is slowing down.
Yeah.
And that's a different matter. So it's still accelerating in its expansion. And we attribute that to dark energy. That is something that the new results that suggest that the acceleration is slowing down actually throw a spanner in the works, because we thought we understood dark energy as what's called a cosmological constant, a force that basically is proportional to the size of space. The more space you have, the more expansion force there is, a kind of pressure, if you like, of space itself, springiness of space. The fact that as time goes on, that expansion seems to be, the acceleration of the expansion seems to be reducing, is it's actually suggestive of new physics, which might mean higher dimensions and all the other good stuff that we love talking about on Space Nuts.
Yes, indeed.
So his last bit of the question, does that mean speed's faster than light? There will be a limit beyond which we can't see the universe because it's expanding from us faster than light can get to us. And that's already the case. But we don't see that because we see the cosmic microwave background radiation first. That's the nearer phenomenon. So, it's an interesting set of questions, which I guess highlighting some of the mysteries that we face with our current understanding of cosmology.
In truth, though, we do not know how fast the expansion rate currently is. We can't put a number on that, can we?
Yes, we can.
Oh, can we?
That's the Hubble constant.
Which is we have talked about that before.
We've talked about it, because there's this tension between the Hubble constant as we measure it now and the Hubble constant as we determine it from the cosmic microwave background radiation, called the Hubble tension, which may be something that really is just to do with measurements. So the Hubble constant's in odd units, it's in kilometers per second per megaparsec, which is basically a fancy way of saying we do know how fast it's expanding.
It is, yeah. The answer is 70 to 74 kilometers per second per megaparsec.
Yep.
Give or take.
That's right. You know, when I was a young astronomer, I keep saying this, back in the 70s, there were the estimates of that number we're out by a factor of 2. There's one group said it's 50 kilometers per second per megaparsec. Another group said it's 100 kilometers per second megaparsec. And look what we've got with the Hubble telescope and other instruments. We've got basically the average of those two, which is quite neat, really. Yeah.
Yes,
But we've still got some uncertainty.
There was also this conflict, wasn't there, that they couldn't figure out the answer for, but we did a story about them figuring out that the conflict was actually normal and that's within acceptable parameters. I think
It did.
Yeah. Okay. Did we answer all his question? I think we did. Yeah. I did look up something else. How powerful was the Big Bang? Greater than 10 to the 68 joules.
Okay. That's what you call a bang.
That's a big bang, but we just shortened it to Big Bang.
I write that down. It's a good number, 10 to the 68 joules.
Yes. Yeah. Put that on your calculator and see what happens. Thank you, Julian. Hope you're well. Let's answer one more question before we finish up today. And this is a question with 47 parts. Hi, Professor Fred and Andrew. Peter here from San Diego, California. I have a dual question about dark energy. My understanding is that dark energy is causing our universe to expand. Also, we have an observable part of the universe where light is able to reach us and an unobservable part of the universe. Funny how we already talked about this, but all these questions kind of dovetailed. Question 1, is it feasible that the unobservable part of the universe contains enough matter to act gravitationally on the observable universe, thus causing the expansion? And question 2, which we'll get back to, same question within the context of the multisphere. Could universes other than our own be gravitationally impacting the expansion of our universe? Love your show. Keep up the great work. Thank you, Peter. Question 1, is it feasible that the unobservable part of our universe contains enough matter to act gravitationally on the observable universe, thus causing the expansion?
Yes, once again, we've got to unpick what we mean by the expansion. So Peter says, my understanding is that dark energy is causing our universe to expand. And that's not the case, as we've just described. It's the Big Bang that caused the universe to expand. But dark energy is what's causing the expansion to accelerate, to get faster.
It's easy to get confused, though, isn't it? Because
it is, absolutely. No,
this is an event with a lot of moving parts.
It is, yes, as you'd expect. It's a universe, after all.
Yeah.
But what Peter says is correct, because as we've just said, there are parts of the universe, well, beyond 13.8 billion light years, which we can't see because what we run into is the cosmic microwave background radiation, the flash of the Big Bang. Yeah. So we know there's universe beyond that, but we can't see it. And Peter's suggestion, is it feasible that the unobservable part of the universe contains enough matter to act gravitationally on the observable universe? And thus causing the expansion. It's actually thus causing the acceleration of the expansion. That is one of the theories that people have looked at, exactly that are we in a kind of local bubble where the density is low compared with what is outside the boundary that we can see, where the density might be higher and hence having a gravitational effect on our local bubble. It's certainly a conjecture that is raised by astrophysicists and cosmologists. So Peter's on the right track there. And then question 2, the same question within the context of the multiverse. Could universes other than our own be gravitationally impacting the expansion of our universe? And I think that is also something that's considered. One of the reasons why people think there might be multiverses it is that gravity itself is, compared with the other 3 fundamental forces in nature, it is incredibly weak. So the fundamental forces are the strong and weak nuclear forces, things that hold atoms together. The electromagnetic force causes chemical reactions and photons so that we can talk to each other. Those are the 3 which are best known. Gravity is the 4th fundamental force, but it is gazillions of times weaker than the other 3. And some people suggest that maybe that is because it is leaking into other universes, hence the idea of a multiverse scenario. But that is very speculative. We don't have any hard evidence that points towards a multiverse. But yes, once again, maybe there are gravitational influences coming from the outside of our universe, whatever that means, because the universe by definition means everything you can observe or understand. So it is possible. So I think Peter's, his questions are well directed. He's on the right track.
Yeah, I think, as you said, there's no direct evidence whatsoever of multiverses, but we've said it before, mathematically, it's plausible.
It's possible, that's right, yeah. A lot of things are mathematically possible that you don't see in reality.
Yeah. And how much of the universe can we not see? Is it like 75% or something?
We've no idea.
We don't know. We don't know how big it is.
Could be infinite. We don't know.
Yeah, gosh.
All we know is what we can see.
It's crazy town, isn't it?
It is, yeah, it is. That's right. It's
keeps you in a job.
Well, yes, it does. Keeps me in a job. That's right.
Yeah. But that's when the critics come out. We got all you blokes trying to figure out, and ladies, what's going on. You've been working on it for hundreds of years, and you still don't know the answer.
We still don't know. The good news is that nobody's paying me now, so that's all right. So you don't have to worry about that.
It's a cost-free analysis now.
There you go. You get it all free. That's right, ladies and gentlemen. This all comes to you free.
Yes, it does. All right. So I think we covered everything there. Thank you, Peter. Great set of questions all up. Some real intrigue in some of those as well, which is really good. But as I've said many times, we need some more questions. So if you can get online to our website and click on the Ask Me Anything tab at the top of our page, send us text or audio questions. We certainly could use some more audio questions. We get a lot from people who might ask 10 at a time. Obviously, we can't run them all consecutively, otherwise no one else gets a bite. But if you've thought about asking a question and you haven't got around to it yet, don't be scared. We don't bite. Well, we do bite, but don't worry about that. It's harmless. We're not venomous. But you can send it in through spacenutspodcast.com or spacenuts.io and click on that tab and send us your question or just a comment. I mean, if you want to add a comment, we can throw that into the show. It's nice to have all these different voices on the air. Send them in to us. Don't forget to tell us who you are and where you're from. I think I've already said that. We are done, Fred. Thank you so very, very much.
It's a great pleasure, Andrew, and I hope we'll do it again sometime.
I hope so too. Maybe in a week, maybe more, maybe less. It's all to do with scheduling and availability and what our wives are doing at any particular time. That's the most significant factor.
Indeed.
Thanks, Fred. We'll see you soon.
Cheers for now. Bye-bye.
Hooroo. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because he's unobservable. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.